today we're going to do a slope stability analysis through a sequence of excavations by two different methods using GTS NX. Our problem will be a 2D model. As you can see here, we will do a series of excavations and get a factor of safety through each stage. This is the procedure we will have. We will go through importing of a geometry, a DXF file, then we'll define the materials, then we'll move on to generating the mesh, assigning the boundary conditions, defining the stages, and finally looking at the results. Here you can see a brief diagram of what the soil properties will be, our three main soil properties, and the sequence of the excavations. There will be 3 excavations. And then here are the materials for our 3 soil layers. We will be using Moore column as our constitutive model type. And since we're working in 2D, they will all be properties for 2D strain. So this is our GTS NX interface. We will start the new project by clicking on New. This will prompt a new window that will allow us to select if we're working on one of the 3 model types, 3D, 2D, or axisymmetric. In this case, we will be working with 2D, and we will leave the units as SI units, but you can change them to any setting you like, be it at the beginning of the modeling or at any other point down here. You can see we're now working in the YX plane, and we see here we have a grid that allows us to draw on it. If we wanted to draw our slope directly on it, this is where you would do that, directly by either drawing or inputting coordinates, and it can be a polyline or square or any other shape. In our case, however, we're going to import the geometry. We're going to import a DXF file. We will then just simply select the file from our folder. And we see here our geometry already has the final shape. So for that, then we can deactivate what would be this work grid to make it a little more clean to see. And from then, we would proceed on to kind of give it a quick inspection. In this case, all the geometry seem to be properly divided, but it's a real good of thumb to use the command intersect for your especially 2D geometries, just to ensure that the program is going to recognize all the boundaries when it's meshing. We will then proceed on to define the materials and the properties. And so for this, we will go to our Mesh tab, Material. This is where we can select which type of material we're going to be working with. Today we'll be working as an isotropic material, but there are other options in the program, as you can see. And from here, the window to the next part would allow us then to select what would be the model type. For this particular tutorial, as we mentioned, we'll be working with Moore column, but you can see all the list of constitutive models we have, including user's supplied material. So we select Moore column. We're basically just going to define the 3 materials as shown in the table previously, and assign the name for each. So the first one is weathered soil, and the values given by the chart are just going to be typed directly in. Now there is a database within the program for defining certain materials, but we're just going to quickly go through assigning the values here. So whenever we're finished, we can just go ahead and click Apply. This middle tab is actually for the saturation properties. In this case, we won't this is a unit weight when it's dry, and then there's a porous tab for when it's saturated. So when we click Apply, the first one is created, and the next ID is number 2, so we can proceed to define the next material. So this is value of 22, and then the nonlinear aspect. And then the last material, the third one, would be just soft rock. Where we then just define the last material. So you'll also notice we have the option for the lateral earth pressure coefficient, and you can actually even do it if it's anisotropic. So we can actually just give it a value of 0.5. And once we click OK, the window's closed, and we see we have our 3 materials created. If we wanted to go back and change anything, you can always select it and just go to Modify, and it'll open the window back up. Everything has been saved. So let's just update the earth pressure coefficient for these other materials to 0.5. And then from there, what we need to tell the program is how is this material going to be used, which is basically how we define a property. And in this case, we would go here to create, and we can see we can create properties for 1D type of elements like beams or piles, for 3D elements, which would be your solids, and in our case, 2D elements, which when we're working with soil, we basically just use plain strain. And all we have to do is match the name of the property to the material we're assigning, and click Apply. And do the last one here, soft rock. And so now we would be ready to mesh, and these properties have been now created that we can assign directly to the mesh. So moving on, we will be now meshing, and we will be then defining the sequence of excavations. So for the meshing, we will go to generate 2D mesh. In our case, we want to use the option for area. In this window, we select the size of the mesh we want to give. We select the property. In this case, the top layers are going to be for the weathered soil, and we have here an advanced option where we can select a different geometry of element and assign the higher order elements. And we can then just select the first geometry, and we can preview the size. We can also unselect. We will then continue with the next sets. Which has the other property. And then lastly, the soft rock. What I also want to do is here in our work tree, we see we have, if we expand, we have like our geometry curves and our mesh sets. What I want to do is also clean this up a little bit, and so basically just go here to the property window and start naming these like excavation 1 to just make it easier to follow as to what is going to be the sequence. So we have our excavation 1, and then we will have This will be excavation 2. This will be excavation 2 sub 1, or excavation 2 sub 2, which is basically also going to be excavated in the same stage. And lastly, our excavation 3. We can now proceed to assign boundary conditions. The program allows you to define your boundary constraints in different methods. As you can see, you can select by a node and assign a particular type of condition. You can also manually restrict displacements or rotations in any direction, or you can just let the program do it automatically, as we see here. So if we go to the workstream next tab analysis, we see now that we have this 3 sets of boundary conditions, and we can see exactly what's being restricted in each direction. We could then proceed to assign what would be the other necessary boundary condition for what is a slope stability analysis by the strength analysis method, which is a hybrid method between what would be the finite element method, the strength reduction method, and the limit equilibrium method, which requires a slip boundary condition, which is basically what we're doing here, a slip circular boundary condition. So we're going to create 2 sets of these. And so we can select first the grid range, and we can draw it directly above. I'm estimating more or less where I think the arc failure is going to be for the series of excavations, so I'm actually going to have to create more than one. So in this case, I can also change the number of centers. And we see now it's been updated, and then I can also then tell it where the tangent line of the circle is going to be. So I can draw what would be the bottom of this for my first excavation, and I'll change this to 6, and I'll tell it here that this is the sand boundary 1, and then I'll repeat this process further down, again trying to estimate more or less where the failure will be at different stages of the excavation. Obviously it's going to change. I'll make this a different size, I'll make it a little more, and then I'll define the new tangent line of the radius range. And this will be my SAM2, my other boundary condition. So we see we have 2 boundary conditions here, and then I can proceed on to assign loads, the first one being like the self-weight. As well as what would be like a water level. Or if we wanted to assign a pressure force, you can assign it directly here. In this case, we're just going to also assign the water level. And all I have to do is select the geometry of the boundary. You can actually draw other lines, other edges to help you define the water level that might not be directly related to a particular boundary condition. And we will now be ready to create the construction stages. So we will go here to create construction stage. We select from the list, this will be a stress analysis, and we add it, and then we can proceed on to define. Once we created it, we select it and define the stage, or the stages. We have 3 windows here. We see the first set is basically our work street, everything we've created up to this point, and then we have what we want to be considered or activated for a stage, given stage, and what would be deactivated for a given stage. There's a trick to help us know what's being considered in each stage, and it's to switch the show data to activate, and we see that nothing has been considered yet. So then as I start to drag and drop from my initial stage, we see things start to appear. So the initial stage will have all the basic grounds, and I will also activate the clear displacement, and this will be, I give it a name of initial stage. And so then I can just save and create a new one. This will be the stage for the first excavation. So I will call this excavation 1. And I will drag and drop to the deactivate window, and we can see that the first excavation is not being simulated. And I also want to have my first slope stability result, my first factor of safety for this excavation. So the program offers two methods, one by the finite element method, the string reduction method. As I had mentioned, that's the classic way of calculating your slope stability using finite element. And then there's this other method, the SAM, strength analysis method, which, as we had said, similar to the limit equilibrium method and requires this boundary condition. So for this case, it does use finite elements to calculate the stresses, and then based on those calculated stresses and the boundaries of the arc failures, it can determine a factor of safety. So this is for stage 1. And then we can go on to see the next excavation, which would be ESCA 2. So I can now drag and drop this other sets of excavations over here. Again, I activate the slope stability analysis, and I'm going to activate again this other method. However, I think in this case, this other boundary condition is more appropriate. And so for me to now consider this boundary condition in this stage, I also have to deactivate the previous boundary condition, since I don't want to have two of them activated simultaneously. The program will maintain something on that has previously been activated. And lastly, I'll go to my third excavation. So I drag and drop the last set. I will now actually simulate what would be the water level. So I can select the water level I had defined previously, the set of geometry, and this value now becomes a multiplier. So I give it a value of 1, and lastly activate these sets. And so we see here when I click save, we can see a small blue line appear. If I was to give this a different value, for instance a value of 2, it's a multiplier. We see that follows the same geometry more or less, but it's now amplified, or vice versa if I was a 0.5 or something. So we see how it's a multiplier, so we just keep it at a value of 1 if we have previously defined a geometry. If we don't select the geometry, this becomes a global horizontal water size. We can see here now it's completely horizontal. It's based on the origin, so it's at a height of 5 meters. And then we would be ready to just define the analysis. In this case, we will go to Analysis, General, Construction Stage. We select the stage, and we can control other things, and the analysis control, like if we want to consider the earth lateral pressure condition, as well as the output control. We want also to see strains in the results. The default is no strains. And we run the analysis. We have to save it somehow as our tutorial, our excavation slope tutorial. And then we can perform the analysis. When we perform the analysis, we will see a output window at the bottom, give us information about the analysis that's running, such as warnings, time of running. So some warnings, like the following we see here for the number, a certain number slip service failing, could give us a hint that we might have to redefine our boundary condition for the SAM boundary. We can see also the progress of the analysis. And if it's converging or not converging. And in the end, we will see how long it took to run the analysis. So I'll just open the finished model with the results. We are now in the post processor. We see that all our previous commands are logged, but the results tab now has the option to see different kinds of results, and our results tab has our results all gathered together. So we can see here we have, if we expand each stage, we have our type of results grouped. We also see that for each of the stages there are two sets of results. We see, for instance, we have our regular stage excavation 1, and then we have the regular stage excavation 1 SRM. What this is the analysis, the program first runs the static analysis, static nonlinear analysis, and then it runs the slope stability analysis. And so we see, for instance, that in the slope stability analysis result section, it's giving us a factor of safety of 2.5. And if I expand on my strains, I can see the arc failure. And if I expand my other results like displacements, I get a concentration of displacements where the slope has failed, and a result of around 40 centimeters. So this is considered what would be the failure result, the different results than what would be a static analysis. If I was to look at the same stage of the excavation and look at the static displacement results, we see that they're quite different, and they concentrate on a different aspect. It would be more what we expect to be normal. And if I was to change my dimensions to millimeters, we see that it's a much smaller displacement. So there's difference in each stage between what would be the static analyses and the slope stability analyses. This one mostly is only important for capturing the factor of safety, whereas this other one can give you results that are important like your stresses or your displacements, or if you have some sort of structural support, you want to look at your static analyses. So we can then navigate through this. We have a bar at the bottom that goes through stages, so you can immediately tell when we're switching between what kind of analyses. So here we have the stress analysis for the second excavation, and then the slope stability analysis for the second excavation. And we see that the displacement has gone now to around another 40 centimeters. And lastly, if we continue to the last stage, again, we're now around 33 centimeters. Versus what would be less than 1 for a normal static analysis. So other aspect of this is the two methods for capturing your factor of safety. So we were looking, these are the SRM results, the strength reduction method results, but we also define by this other method, the strength analysis method, and we had our own boundary conditions. So for that we have to go to our special post processor. And here we can see now for the different stages and the different sets of boundaries, we can actually just tell it we want to see the minimum automatically. And we can see there that it gives us our familiar arc, kind of like an limit equilibrium method, and it looks very similar in that respect to the results from the strength reduction method for that stage. And we can compare it, for instance, to the last stage. And we would then switch to a different stage here as well, to the other boundary, and we see that it also lines up quite nicely. And what we see at the bottom as well here is the results by the two methods. So we can see for the SAM method in stage 1, for the SAM and the SRM method in stage 2, and for the SAM and SRM method in stage 3, and they all match pretty clearly, 2.5, 2.3, and 1.5 in each stage. So you can also see other results like stresses, principal stresses. You can see other results like your pore pressure. And if you had some sort of support, you could see beam or stress. That is the conclusion of this tutorial. Thank you.